Here is about a little project that I've been playing around for a while. On the left, you can see a transformer architecture, the bedrock of the modern AI revolution, generative AI revolution that we are experiencing today. On the right, we have some data set. So where each line represents a story. So a story is approximately 800 words, and I have 2 million of such stories. And this is a research paper about the stories where authors try to figure out building a small ChatGPT kind of thing with only a million parameters. So it's not really a small paper. It has, 27 pages. Yes. So let's see. So the intention of the project is to create a model that understands and learns a hidden pattern in a given stories. And finally, when given an input, the model has to generate a story. So something like this. Let's give some input and ask it to generate a story. Yep, so the model came with a story. So this project is more like creating a mini version of ChatGPT. So let's see in detail how the model does this magic. So before going into that, we all need to be aware of this paper. Attention is all you need, which was released in the middle of the last decade by a set of Google engineers. So where they are discussed about this model's transformer. So this whole paper in itself is brilliant, and it was originally designed for language translation purpose. But if you ask me, what is the most brilliant part, I would say the attention. Yeah, so this is the most brilliant part of this whole paper. And even the authors have given some visuals trying to explain what happens inside the attention. But to be honest, in the first go, it was super hard for me to understand what happens inside the attention with all its mathematics. So I had to go through a lot of research papers and YouTube videos to understand what's happening inside. And I have made a small presentation out of it. Yep, let's say we have a word or a sentence, I'm a robot. So basically, we convert everything into the numbers and numbers into embeddings. So these embeddings represent the numerical representation of this data. But these embeddings doesn't have more information about its position. So I being in the first position, in the third position, or in the fourth position changes the context of a given sentence. So we need to somehow embed the position in the embeddings. So how do we do that? So using sine and the cosine waves, something like this. So using sine and the cosine squeaky lines, basically we can find the unique positions, unique numbers that represent the position of each given word. And if we add these positional encodings and embeddings, we get a final output. And even the positional encodings doesn't represent the relationship of each word relative to its neighbors. For example, am being present in a second location with these neighbors form a different context compared to a different neighbors. So how do we capture those relevance? And that's where the author's genius come out. So they thought we could introduce something called query, key, and value. So basically, these three are curated from the positional encodings, and they have their own weights, but those weights are same for all the given words in the sequence. And once we have the query, key, and the value, we multiply a query. We take in a query and we multiply it with its own key and all the other keys in the word and form a final dot product. And we apply softmax formula to get an output. So these outputs represent the relationship of a given word to its neighbors and to itself. For example, the word I is more relevant to I itself, so that's why it's having a bigger number. And I is somewhat relevant to the second number, second letters and the third letter. So there are some small relevance, and for the fourth word, there is no relevance at all. So finally, we multiply the softmax with the value to get a unique output. So these output represents the position, the numerical representation of the data, and its relationship to the neighbors in a given sequence. So this is the most smartest thing that's happening with attention itself. So let's go and see what's happening in the code. Yep, we don't need these pictures anymore. Yep, so these are some of the basic libraries that I've been working on. So mostly Tarsh and sentence piece for data preprocessing. So I took in only one data here, because I don't want to complicate the training process. So I just want to see what's happening with one story. So I took only one story, and this is basically a data preparation. So the output, if you see, the beginning of the sentence and the end of the sentence is added to any given one and tokenized. So any given story, something like this, is tokenized into smaller portions and given some kind of IDs for it. So once we have the IDs, we want to convert those IDs into tensors, because it's going to be processed by the torch. And it is a modeling part. For the modeling part, we have the multi-hit attention. So I was telling about this one. So basically we can split the embeddings between multiple heads, so that allows a parallel computing, so which is much faster to train with the GPUs, with the powerful GPUs. So that's why we have multi-heads. So I took 8 heads for my model, and basically it does all the calculations for computing the queries, keys and values, and also the final output, which would be used for adding it to the residual connections, and some basic functions that needs to make this model alive. Splitting the heads, finally combining the outputs of the attention into one value, and the forward function takes care of all these things. And we have a class for push and wise feed forward, and a positional encoding, and a decoder layer. All the masking and all the input masking happens in positional encoding part of it, and decoder layer basically is the whole layer in the architecture. So let's assume this whole part is one decoding, and basically you can have more layers of decoding. I took 6 decoding layers for my training, and defined all the necessary formulas, and finally a class for transformers itself. So once we have all the model ready, so time for instantiating the model, and this is my basic parameters. I have given 512 dimensions, embeddings for each word, and I have 8 multi-head attentions, and we need to be sure that these dimensions and the heads are divisible. And I have 512 hidden neurons to reduce the complexity. I don't want a bigger neuron size because my computer can't process that much. And I did it for 1000 epos, and this is an output that I got. So basically after 300 epos, the model stopped learning much. So this is the inference part. So given the word she, I wanted to generate a story. So on the story looked something like this. She, a little girl named Lily, found a needle in her room. She knew it was difficult to play with it because, okay, so this story is not making any sense, but obviously it is trained on one story, and for one story, it kind of finds a pattern really good. So it understands what words need to come first and what word needs to come in relationship to the previous word. And overall, the construction of the story is somewhat better. So I've tried with different parameters here. So this is the one that I've showed you, the same parameters. So I have tried to increase the epo size, and this is the output I have seen. So the top one is for 100 epos, and this one is for 1000 epos. So for 1000 epos, I see the construction of the words are quite better. Lily in her room, she could see a little girl named Lily found a needle in her room. Okay, so it's not that great. And I try to include more stories. I increased my data size to 1000 stories this time and kept the other parameters quite same. And I trained for only 10 epos this time. And to be honest, trained on more amount of data, it forms a better story. So once upon a time, there was a little girl named Lily. She loved to play outside in the grass. One day, she found a big green trees. Okay, something. So I tried to increase the story size even much higher, but I do not have enough computing power, so I couldn't do it. So some of the other team members were able to train the whole model, a similar model with 2 million stories, and they have came up with some really awesome, good predictions. So I'm going to show you now. So the input was something like, once upon a time there was a bird, and the output was like, it flew high in the sky and landed in a tree. The bird was very happy and flew around looking for something to eat. So it talks about the bird. It clearly understood what bird does, and it has created a story relevant to that. And once upon a time there was a dragon. He was very strong and could fly high in the sky. So dragons can be strong and can fly high, which is also sensible and reasonable. And once in a while, it made some irrelevant predictions. And if you see the other one, once upon a time, there was a little girl named Lily. She loved to play outside the park. One day, she saw a big scary dog. She was so scared that she ran to her mom. And it was, again, makes a good sense to me. The ancient castle around the kingdom, it was very special castle, and it was the most beautiful thing anyone had ever seen. So again, it's really nice. It was all some other sensible stories. So this was interesting. So you can basically go to my GitHub and see my working code and all the relevant data that you need for it. So this is the architecture of my model. So I have used the 6 decoder layers with all multi-head attentions, position-wise feed forward, and normalizations with dropouts. and all the linear layers included. And yep, so what's for future is generating long sequences with sparse transformer. This is another research paper by OpenAI. So I had a chance to go through this research paper. So what basically this paper does is, for example, in this one, I have given an input, I'm a robot, which is a really small sentence. Let's imagine a bigger sentence like this, the whole story. So we have hundreds and hundreds of words like this, and we can't be processing all the information because for any given word, the query calculation is super high. So, and I have given an embedding size of only 4 here, but GPT-2 has relatively 12,000 embeddings. So the more embedding size with a much longer sequence, the computation becomes super high. So basically we need to find a solution. The solution is called sparse factorization. So what is sparse factorization is actually creating a subset of a data. It could be fixed subset and masking the rest data. So it could be like, I don't want to take the first 2 words, take the third and the fourth word and leave the rest 2 words. Or we could install a learnable matrix that understand what words are relevant and ignore the rest. So this way, we can reduce the computational complexity when it comes to increasing the token size. So this is something that I kept for the future. But yeah, this was all about my project. So thank you for your time.